right, thank you, and for your patience as well. I'm learning that I should carry all dongles with me, but in this case, I don't think it would have helped. So, all right, so I'm gonna kind of speed ahead here. You'll notice that I still have my Haskins affiliation, and that's because once you're with Haskins, you're always with Haskins, which is a good and a bad thing, but I am still affiliated with Haskins. So I'm talking about perceptual learning across a variety of individuals. As Chris said, my initial work with what we consider officially perceptual learning, that is work with infants, speech perception, was with typically developing infants with Jim Morgan at Brown. And from there, I went and did more infant research with speech and with all sorts of visual processing issues. And in the course of doing that at Texas A&M, I got to know a surgeon who was interested in another technique I was starting to work on, which was functional brain imaging with an infant-friendly technique called near-infrared spectroscopy. So my perceptual learning, kind of interestingly, became quite relevant, but only after we got excited about using NIRS with the kids, functional near-infrared spectroscopy, did I realize, boy, pediatric implant users are a really interesting case of perceptual learning under duress or in a very different sort of situation than a typically developing infant is in. So I feel like I've kind of come full circle back to the original baby work I was doing at Brown in this research. So why cochlear implants? Well, as you all know, of course, around the time I moved to UConn, we all had to start doing much more translational research. So there was that practical force behind what I was doing. But also, I met John Ogleye, the surgeon, and it was sort of like I had the right tool for what he wanted to do, which was to look at whether he could program the implants for these kids more effectively. So deafness is the most common, well, it's one of the most common developmental disorders and definitely the most common sensory disorder in the US. And it's controversial, but cochlear implantation is now the default treatment in the United States and most developed countries at this point. And obviously there's a whole interesting line of controversy about that, and I'm starting to get more and more involved in the research on that side of things about whether Sine is appropriate to use with the kids or not. But, and I'm happy to answer questions about that, but really I'm interested in the perceptual learning side given what these kids do get. So let me just walk you through a bit what implants are. So this was, as Chris said, this is considered really the first brain-computer interface that's been widely distributed and used. So this was a National Geographic issue on bionic bodies. And so implants were featured in this. And so here you see a bilaterally implanted toddler, and he's got both the implants. This is just an X-ray. What's nice is you can actually see the electrodes in the cochlea there. I also like it because it gives you a perspective of how small the cochlea is relative to everything else in the head, even though it's the driver of everything that is language-based, spoken language. So how do they work? Well, basically you pull back the scalp, and this processor is embedded in the skull. They kind of Dremel out a little bit of the skull and put this processor in, and then thread the electrode into the first basically the first turn of the cochlea. And so information is taken from the outside, right, by the speech processor, transmitted to the internal processor, and then a whole lot of fancy processing, of course, happens for it to be divvied up across the electrodes that are in the cochlea. And the idea is each electrode conveys a different frequency band and ultimately stimulates the auditory nerve. Just bypasses the hair cells entirely, because that's the problem with these individuals who qualify for a cochlear implant. Their hair cells are not working. So here's an much older implant, and I just like to show the evolution of this over the last 20, 30 years is really remarkable. So this is 12 electrodes, and now we're up to 26. The max is 26. Usually people are implanting with 22 or 23. So here's a more recent implant with a lot more electrodes. And you can imagine the engineering involved here is on all sorts of different levels really interesting. But one of the issues is if the processor's turned up too loud, the signal's too high, you get crosstalk. So there's a lot of different things that have to be done in the programming of how the speech is processed to even get it in the right form to those different electrodes. And just to highlight another interesting aspect I think a lot of people don't realize is, this thing gets threaded up into the cochlea, and you can't thread it too far without damaging the walls of the cochlea. So it only goes up into that first turn, which means that all the speech that's conveyed across those electrodes is sent into a part of the cochlea that is high frequencies, right? Because the low frequencies are up there. And so basically, anybody, an adult who gets an implant who's postlingually deaf, when they get their implant turned on, say that everyone sounds like Daffy Duck, because everybody's voice is up in this high frequency range, which is kind of interesting, I think. So there's all sorts of crazy perceptual stuff going on, but they apparently adjust to that quite quickly. So what does the signal look like? This is another thing that's quite hard to actually demonstrate, because the signal is in their head, and so when I try to generate a spectrogram of what the signal looks like, it's on simulated speech, and we don't actually know if that's what it sounds like, and it's going to sound different to each individual depending on their electrode placement and all of that. But roughly speaking, so here you have the amplitude envelope of the speech. Here's a normal spectrogram. We're looking at the lower frequency range here where speech is really carried. And critically, what I want to focus on is the fact that all those transitions that you have in the formants that carry so much information, both spectrally and in the fine temporal detail, is pretty much wiped out. It's because it's bandpass filtered, right? So you basically have channels of frequencies. And so all that nuance that presumably is what we're using when we process speech is flattened out. So that's interesting and poses an interesting problem. Right, and I like to show this just to, keep people in check. A lot of people don't know who he is anymore, but or at least they've never seen his face, but I'm going to scare you today. So Rush Limbaugh, our favorite complainer about federal government spending money on things like, medical research, is actually a user of two bilateral, he's got bilateral implants because of the OxyContin abuse, because guess what? Kills hair cells. So what's interesting is that he never missed time on the air. Basically, he went and he got his implants sequentially, and most people had no idea there was anything wrong, but he's like deaf now, and basically has been using implant. You say, how can that be? Because you hear about, well, with pediatric cases, some kids don't learn language very well, some can't process very well. Well, the difference is he is postlingually deaf, right? So he has all this information in his head, however you want to call it. I'm going to use the dirty word. He has representations, I don't know, something in there that came with learning language, and he's able to just put it right on top of that degraded signal he's getting from the implant. That's a completely different situation than when you're a little kid learning language for the first time through this degraded signal, right? And that's really where the interesting stuff is, I think, with implants. And so that's why I was attracted to this collaboration with John Ogilvie. Now, even in the last 10 years, we've gone from little kids like this, who you can at least ask to tell you what they're experiencing. Here he's doing one of these behavioral training things where the child gives a token every time they hear a sound. There's all different kinds of behavioral tricks to get the child to tell you what they're hearing. But it's gone really rapidly to a much younger age, because just to show you the neuronal morphology, the auditory cortex, obviously we see the usual synaptic growth, pruning back, and most people are used to seeing this in the visual cortex, and a lot of the business happens right before 6 months. Auditory cortex is a little bit slower than that, so you see this huge amount in 6 months, and a little bit of pruning, and then another big surge right around here, which is really where the complexities of syntax and so forth are kicking in. So obviously it's important to get the implant in, before this whole process is done, but really this is where you want to be, right, where that perceptual learning is happening. And just to add a little bit of weight to that, folks obviously in speech language communication departments have been studying this for a long time, and Michael Dorman in particular has done beautiful work showing using the central auditory evoked potential, which isn't a speech-based measure, it's just a sound-based measure of the central auditory, the functionality of the central auditory nerve and how well it's conveying information. Basically, if a kid's implanted before 3.5 years, their P1 latency, which is this gold standard, the central auditory evoked potential gold standard, needs to fall within these 2 lines, within this banana curve. And they do if they're implanted before 3.5 years. As soon as you start getting later, what you start seeing is that P1 latency starts not looking typical. And if a kid's implanted after 7, they're, all bets are off. And generally those are the kids that don't learn language very well from this signal. So obviously the earlier the better, but 3.5 is still, imagine not getting any auditory input until 3.5. You're probably not processing it like a typically developing kid, even though you're getting it supposedly in this window of time. Now these are just little pips of sound being delivered, and you're measuring electrophysiological response. And you'll see why functional neuroinference spectroscopy was of interest to use to supplement these kinds of data for that reason. But so given the neuronal morphology, a lot is happening from 6 months to 12 months. So this is what's happening. This is a 6-month-old bilaterally implanted. And John, I actually just met with him last week, and he said he just did his first 6-month-old, implanted his first 6-month-old. That's a whole different surgery because their skulls aren't even fused yet. But this is the direction things are going in. So you can see why the issue of using Sine or not starts being almost, I won't say moot, but it's something that's sort of secondary to the signal processing and tuning of the implant. Okay, so the critical issues here are, how do you tell what this kid's hearing, right? And whether the implant is conveying sound appropriately. So you have to tune each individual electrode, and presumably that's based on some sort of feedback from the child, right? And then, of course, is the child actually using the signal to learn language? So, oops, sorry, let's go all 3 of the approaches here. That was an animation fail. So the different approaches I've been using are first to use FNIRS just to see whether or not we can get speech evoked activation patterns from cochlear implanted patients and compare them to typical hearing adults and children. So both populations are of interest, right? And then, of course, once you get there, does the activation pattern load onto some sort of measurable ability, perceptual ability? Because that's really the goal, is to use it as an indicator of whether or not a child is processing the sound well, right? That's the goal. The goal is to get to the point where we could use it in a predictive way to help in the clinic. That's a long way off, but we have to establish this first. And then finally, to go, as I was saying, full circle back to the perceptual learning issue, we're really interested in the degree to which this tells us anything about how kids typically learn language, how much, there are long-standing debates about the degree to which kids have access to phonemes, phonetics, how much spectral detail do they really need, and it actually has opened up, this whole line of work has opened up a new line of research for me in terms of looking at the spectral and temporal influences on processing, which has been really satisfying. It's just like bypass the whole phoneme thing entirely, because guess what? There's a whole lot of stuff in that signal, and you can use what's there. Whether it's all there, that's great, but even when it's not all there. And so that's a whole other line of research I've been working on with Jean Vroomen, who's a researcher in the Netherlands. Okay, so I'm going to walk you through this pretty quickly. We didn't start too late, but I don't want to go too slow here. So I'll show you some of the early data, which actually are only about 6 years old at this point, but it feels like a long time ago. So this is John doing the surgery. So what we were interested in is collecting data from the kids. We're ideally going to look at kids, right? But what does it look like, the auditory activation pattern from adults? And what about kids who've been using their implant for a while versus kids who only just got activated? Do you see changes over time in their cortical activation pattern? So we're using FNIRS. Some people just call it NIRS. I tend to call it NIRS, but it's near-infrared spectroscopy, and it's poor man's fMRI. Here's one of my, this is my first machine, which is pretty small, but it works just fine, and that's nice pulse rate, signal from my head, which is the indicator that you've got a good signal. So that's what we're going to use here. Let me just really quickly tell you how FNIRS works. You're taking a series of coupled lasers, and each coupling has a laser that's in this lower wavelength range and one in the higher wavelength range, and you're ideally targeting this changeover in absorption of these wavelengths. So what you want to do is target the differential absorption of that oxygenated and deoxygenated hemoglobin bring to the scalp, so, or to the cortex, right? So you're basically just measuring the modulation of light intensity while different stimuli are presented. So everything's time locked to the stimulus that a person's being presented with, whether it's visual, auditory, whatever. And just to show you what this looks like, so you have a laser coupling and a detector, and so the light is shining through the head, and you're measuring the how much of the light has been absorbed, how much is reflected back out. And the idea is, of course, the light scatters throughout the brain, but you're able to get some basic measure right next to it, about 2 centimeters to 3 centimeters, depending on the age of the subject and the thickness of their skull. And you know, ramp this up to a whole head probe, and you can actually start doing some localization changes in blood flow. And just to show you the way these measurements work, so fMRI is really based on the bold blood oxygenated level dependency is based on deoxygenated changes. And what's interesting about NIRS is you're getting both the oxy and the deoxy measure. So you actually have a more robust signal in a sense, in that, you know, I mean, you've got to have both those things showing to demonstrate a change. And what's interesting is a lot of the basic research with NIRS is looking at physiological details that fMRI really doesn't allow you to have access to. That is, people, you know, who are able to do work with the animals, for example, and just remove the skull, and you can get really, we can't do that, obviously, but you get really beautiful physiological data with NIRS. Okay, so this initial study, we normed on normal hearing adults, but then we looked at normal hearing children, deaf kids who'd had their CIs for at least 4 months, and deaf kids the day of activation. And the stimuli are really, really simple. Basically, they're hearing continuous speech, kid stories, and they're in 20-second blocks with variable baseline, no stimulus intervening. And so this, like I said, this was my very small NIRS machine. So basically I had a laser and 2 detectors, and I was able to measure both hemispheres, but really just center the probes right over auditory cortex. And the resident, Alex Hubby, who ran this, had created this whole headband, and it looks ridiculous, but it actually targeted really nicely the superior temporal regions of the auditory cortex. So Mike Beauchamp did the fMRI with our stimuli to verify where the activation should be. And this is running speech with complex meaning, so both hemispheres are actively involved, which is what you would expect. So here's a little boy with a probe on, so we test him in a sound booth. And what we did to keep the kids entertained is we had Animal Planet going without the sound on. So the kids are just watching Animal Planet, and the audio's coming on and off, right? And their parents sitting there with them. All right, so just to give you a rough view of this. So in this case, red is right hemisphere, blue is left hemisphere, and we have our predicted oxygenated and deoxygenated response. And just to show you, we get a pretty nice bilateral activation in adults, normal hearing adults, likewise in normal hearing kids, likewise in the deaf kids with cochlear implants who have used them for some time. But what was critical is that the kids on the day of activation didn't show robust bilateral activation. They tended to show a really nice oxygenated response, very flaky deoxygenated response. And, you know, those two systems really work together, and so it's not surprising in the auditory cortex, never been stimulated before, you're going to see some physiological ramp-up time, and that's exactly what we're seeing. The deoxy on both hemispheres was a little slow, not at all predictable, but we did start seeing at least a nice response in one hemisphere. And the reason that's of interest is, I'm not going to worry you with the details here about, you know, obviously we have huge age ranges, and some of the people we couldn't get good signal from. But of those that we got a good signal from, I want to highlight that. And the other thing is, some kids have a right hemisphere, a right implant, some have a left implant, some are bilaterally implanted. So if we focus just on the kids that are right implanted, and of course the right side is typically where to go with the implant, because the idea is language is on the left, so processes contralaterally, and so you should put the implant on the right. What's interesting is, so if we just look at the right-sided implants, the deaf kids at activation don't generally show a contralateral response. They show an ipsilateral response. And then you start actually seeing a switch, so that, so the ipsilateral response is at day of activation, and then you see the switch to contralateral after they've been using the implant for a while, and the idea is, okay, so the information is getting shuttled over to the other hemisphere, or at least at a very low level. So it starts pointing to some laterality consistencies, or at least that you would predict. We didn't make a lot of these data for obvious reasons. It's really messy, but it started pointing to some processing, some predictable responses that you would want to see with increased use of the implant. Okay.
Can I ask a very quick question?
Yes.
So was there a non-language related sound control?
No, we didn't have a non-like. You know, that's a great question. This is like early days, and so the study I'm going to talk about has all that sort of data. All right. So now the question is, what about speech perception? Whether the quality of speech perception? Because we were just looking at the amount of time using the CI and laterality responses in the cortex. And obviously in those early implant data, we don't have any language speech perception, because kids, when they just get turned on, and you know, it's kind of it's a big deal. You don't go in and try to test any specifics about speech perception at that point. So what we decided to do, and this is what we've been doing for the last several years, is to start teasing apart this issue of different stimuli and the quality of speech perception performance in adults, because they're easy to test. And the idea is now to bring this down to kids, right? So in this paradigm, what we did, we still have the 20 seconds on, 20 seconds off, and now we're at a point where we're shortening that, doing much more like event-related designs, because this is just too costly in terms of the amount of time each stimulus set takes. But we have normal speech, and then we're presenting channelized speech. And channelized speech is basically what's called vocodin speech. It's as if it were processed through a cochlear implant. So this is the simulated speech that if you hear somebody say this is simulation, this is what it sounds like, right? And just to show you, we're taking only up to 8,000 hertz, because that's about what you focus on with a cochlear implant processor anyhow, is you want to get the speech signal. You don't want all those higher frequencies. So you take that, and so what you should notice, it almost looks the same, but the spectral detail is kind of muddier here. It's flattened out. And then the control condition is scrambled speech. Basically those channels all mixed up, so it doesn't sound like speech at all. So this sort of sounds like speech. This is natural speech. And then we have a condition of environmental sounds, like all sorts of animal sounds and car sounds and so forth. Okay, so we have bigger machine at this point, so we have bilateral measurement, pretty good coverage of the auditory cortex. And I'm not going to worry you with the signal processing. This is another thing that's taken a long time to standardize and be happy with, that we're not biasing, we're not cherry picking, any of that. So we have a good system set up at this point. Okay, so we've got control subject and we have cochlear implant subject. These are all adults, right? And they're postlingually deafened adults. Okay, but even postlingually deafened adults do better and worse with their implants, which is an interesting issue because they've got language. So if they can't use the implant signal, it's got to do with the way the thing is tuned and the way it's laid into the cochlea itself. But what we see is the normal and the channelized, the controls, these are hearing individuals, show nice, robust activation. Less so for the scrambled speech because it sounds awful. And then environmental sounds a little bit less. And this is consistent with the fMRI research on environmental sounds. You get some activation, not as much as with speech. Okay, and then the hemodynamic response is the deoxygenated response corresponds appropriately. So we like to see that the controls looked like you would expect them to look, like they look in a functional magnetic resonance imaging kind of study of this nature. So now, if we look at the CI users, we'll just for now pick one good perceiver and one poor perceiver, and we're using the standard consonant nucleus consonant test that speech language pathologists use for this. And what you'll notice is with the good perceiver, so their scores are good, and their patterns of activation show more activation to the speech signal, a little bit less to the channelized speech. Now imagine they've got an implant, so they're processing channelized speech into channelized speech, so it's probably a lot more degraded for them than it was for the typical hearing individuals, right? Much less for the scrambled speech and not a lot for the environmental sounds. And remember, implants you can tune them to different signals, so they're maximally tuned to speech and not to stuff like environmental sounds. You don't want that stuff, which is one of the whole business sides of implants, is coming up with programs for music, for restaurant settings. Really, they don't work that great. So most people just say, give me the speech one and I'll just keep it in place. But that's, I think, what you're going to see in the next 10, 20 years is better performance on those kinds of things. All right, so here's a poor perceiver, and this is what's interesting. You might expect, well, that they're not hearing the signal well. You might just see low activation across the board. But you don't. You see the same amount of activation across all four conditions, indicating they don't know what they're hearing, right? And they're working hard to try to hear it. And it's kind of counterintuitive, but I think really an interesting demonstration of what happens when, it's not that it's noise and my brain can tamp it down because it's noise and I think it might be speech, so your brain's actually ramping up the effort to process it. You can imagine how frustrating that would be. What we did, it took us a long time to figure out how to quantify these different conditions and the effects. So what we did is we used the scrambled condition for each subject as the baseline, right? So we normalized their response to the scrambled speech and then looked at the relative activation to the other conditions, okay? So in the controls, you see, you get nice left and right oxygenated, deoxygenated response like you should for the normal speech. For the channelized speech, scrambled speech doesn't sound like anything. That's what we're using as our baseline. And you see the environmental sounds aren't any different from that, right? The good perceivers look very much like the control subjects. The poor perceivers are consistent with those activation maps that we saw just across the board, not showing differential response to the different stimuli. And importantly, then we do an activation area ratio of normal speech to the scrambled speech. And if we plot that against the standard speech language pathology scores, so the consonant nucleus consonant words, and then the AZ bio is another test, and these are both oxygenated in red and deoxygenated in blue, what you see is the better they do on the score, the more their activation in response to normal speech relative to scrambled speech, and that's across the board, which is nice to see, right? Now what you might be wondering, at least the speech-language people in the room might be wondering, what is it all about speech reception threshold? Because it very well could be that it's all about the, basically, what's the gain? How much signal are you getting? Well, if we plot that activation area ratio against their speech reception threshold, you see no relationship. So it's not about that. It's about how well they're actually getting speech out of the signal, which is a good thing to know. Okay, so that, we're really excited about this work, and we're now running kids with this sort of paradigm, and trying, of course, their behavioral scores aren't as reliable, but you know, that's the direction we're going with this. In one direction we're going in. Okay, so, and the goal is to figure out what sort of experience this individual is having. But another way to look at it, and the last set of data I want to show you, is what this child's experience might tell us about what this child, a typically developing child, is experiencing. And likewise, how flexible is this kid should tell us quite a lot about the degree to which you don't have to have a perfect signal to learn language. Right? So this is work that was published in Cognition, and then we just did a follow-up with a little bit older kids, and we're doing more of this kind of work. But what's interesting is that my interest in multimodal processing were completely independent of the cochlear implant work, and there's a lot of interesting effort in the adult literature, speech perception literature, to tease apart the spectral temporal issue. And the way that people do this is often with a stimulus called sine wave speech. And you know, this is an old Haskins trick. Robert Merced has been using it for, well, since the 80s, right? What's interesting about it is it strips away the spectral information and leaves temporal information. It's not perfectly orthogonal, but it works pretty well. And so what I was interested in doing is seeing the degree to which kids can use the temporal information in speech without all that spectral information and still do pretty well with it. So together with Jean Vrooman and Martijn Bart, who was his student, who's now a postdoc at the Basque Center in San Sebastian, we really wanted to look at the degree to which kids can use temporal information to ultimately, I don't want to say understand speech, but recognize signals that go together in a multimodal world. Okay. So obviously we know a lot about auditory processing and isolation in kids perceptually tuned to speech, kids perceptually tuned to all sorts of visual stimuli, including visual speech. But what about multimodal evidence? Because the reality is they're processing speech in a multimodal world, and so we want to take advantage of that. So what we did is we used sine wave speech, and we're testing adults and infants on more complex stimuli than infants normally get tested on. And as I said, sine wave speech, basically you're just taking this sinusoidal tone that traces the center frequencies of the first three formants of a word, and you're stripping everything else away. That's all there is. And it sounds a lot like vocodin speech or like cochlear implant simulations, which is just a fluke. But you know, it turns out Shannon, one of the people who created cochlear implants, or really was behind the advancement of cochlear implants, has a whole science paper in the mid-90s on speech perception through temporal cues with no spectral information. So independently, we were trying to do this with these infants, so it's kind of, that's the full circle that the cochlear implant work is actually quite relevant, and vice versa. So basically with this sine wave speech, you get the temporal dynamics, but it doesn't sound like speech unless you know you're listening to speech. And so what, so the original study by Robert Merced is that you can play the sine wave speech, and people will say they don't know what it is. And then you play them the original speech that it's derived from, and then they can't not hear it as speech. So it's like you get cued to encode that signal that you heard on this degraded signal. And then once you're in that speech mode, you can't not be in speech mode. But what's compelling about it is the degree to which people are resistant to going into speech mode. They don't hear it and think, oh, that sounds like speech. They just think it sounds like computer noises, right? And so Jean has followed up, Jean Bruman and his student on this. And so Martin Bart came and did a postdoc with me on he had a Fulbright grant, and we did this work at Haskins. So what we did is we use sine wave speech, we use more complex words. They're not terribly complex, but they're trisyllables, which is complex for kids, because we're going to run this on kids as well. So the words are Kali, Su, and Mufapi. So they're non-words, but they're maximally different in terms of place of articulation. So Kali, Su versus Mu. So Mu's in front, Kali's in the back. And we basically have the same speaker producing the words. And what the adults are getting is one or the other stimulus, Kali, Su, or Mufapi. And their job, it's a 2 alternative forced choice task, right? And it's between subjects, so they're either hearing the natural speech or they're hearing sine wave speech. Just have to push the button. What does it go with, this or this? And obviously, natural speech, this is a really easy experiment. And you might think, because they're looking at faces, the sine wave speech would be easy too. Like it would cue them that, hey, this is speech. But what you see, here we've just been first half of experiment, second half of experiment. See, they're great at natural speech. They're above chance, but not great at sine wave speech. Okay? And if you've been in further, you see there's a bit of a learning effect for both conditions, but it really, asymptotes out and they never get really good at the sine wave speech. And if we look at individual subjects' performance, first half of experiment, second half of experiment, you see, there is some variability. Some people really stink, and then even with the natural, they're like, what's this experiment? And then they max out, right? But what's interesting is you see a lot more variability in the sine wave speech. And some people, oh yeah, okay, second half of the experiment, this person got it, but a lot of people just stink. They have no idea they're listening to speech, even though their job is to basically put the sound with the moving mouth, right? So basically half of our subjects performed a chance on this. And so we thought, well, maybe the high performers figured out it's speech, but nobody identified what it was, the sounds, what the words were, Kali, Su, or Mufapi in the sine wave speech condition, right? And even the really good performers still were significantly worse than the good natural speech, than the overall natural speech performers. So that's not particularly exciting because these are adults. They know phonemes. Sine wave speech is spectrally super degraded, right? So the question is, what are infants going to do? So we had 30 infants. Again, it's between subjects, and we tested them with a preferential looking paradigm. Same setup as the adults, but now we're measuring who they look at rather than their button pressing. And so they get a visual familiarization where they see that both screens are in play with no sound, and then the sound starts. And it's Kali, Su, or Mufapi, and it's either in natural speech or sine wave speech, right? So roughly, you see that they both do better, both conditions do better. That is, they look at the matching face more than the non-matching face. And what you see is it's comparable, their performance, but importantly, it's not great. It's above chance for both natural speech and sine wave speech, but it's not fantastic. And the reason this, I think, is interesting is not, people say, well, so the kids could do well with sine wave speech. They did as well with sine wave speech as they did with natural speech. And that's one way to look at it, but a more compelling way to look at it is that they actually do really badly with natural speech. So here we've been told all these years, based on Kuhl's work and Jenna Worker's work, that kids do multimodal processing, no problem. They're able to integrate audio and visual signals. But the reality is, as soon as you ramp up the processing difficulty, as is the case here with 3 syllables instead of it just being a CV syllable, they're really not doing that well. But they're doing well enough that they're performing above chance. What's interesting is the individual variability is huge and completely comparable across the two conditions, right? So we get 3 infants in the speech group and 3 infants in the sine wave speech group performing below chance. And you could say, well, actually, those might have been the really smart, tuned-in kids, and then showing a novelty preference and looking at the unmatched face. But, you know, that's an infant testing debate. Okay, 3 infants in the natural speech group, 4 in the sine wave speech at chance, so comparable, and then comparable numbers performing above chance, right? So what we argued in the cognition paper is that demonstrates that kids can use just temporal information. They don't need the spectral information because they perform no differently in the sine wave speech condition than they did in the natural speech condition. So here for years, all this weight's been put on them getting this representation of phonetic information built up in their head, but maybe it's something a lot more low level than that, like the fine temporal structure that they're getting across signals out there in the universe, right? Visual and auditory, particularly in this case. So rather than it being all about phonemes, it's about them trying to track stimuli in their environment. Why this is relevant to cochlear implant users is it shows that with appropriate support in the visual domain, they should be able to make sense of this degraded spectral information pretty well. Right? It's not ideal. You'd rather have the redundancy, the spectral information as well. But if you don't, you can still perform. Now the issue is getting them up to the natural speech at ceiling performance, right? But I think this is just an interesting demonstration of the degree to which kids are really pretty flexible. And that's why you see some kids with cochlear implants doing really, really well. Of course, there are plenty that don't do so well. But it also speaks to the importance of early implantation. And I think ultimately in terms of our understanding of speech processing, early speech processing, it starts showing that we put too much emphasis on our ideas about how speech is represented rather than looking at how kids are really just using what's out there in the environment to use that signal across the course of the first few years. So that's what I've been doing, and I want to thank obviously John Ogilvie, the surgeon at Stanford I work with. Mike Beauchamp does all of our fMRI work, and Martijn is now at BCBL, which is a great place to do a postdoc. And Katie's my student still at UConn, and Jean Vrooman's in the Netherlands, and he's the sine wave speech guru. So thank you.
Plenty of time.